Well, yeah, we'll move into our instruction sets. This is kind of we're going to do our little dots challenge recap. So yeah, once again, the challenge was to recreate the best performing version of Conway's Game of Life that you could. Real quickly, I'm just going to go over what I did for the challenge. So when the challenge started, I was actually traveling, so I did kind of my initial implementation of this just while I was on the plane here.
Oh,
Yeah, I did some just kind of basic grid spawning on the first flight here, and then let's see what else did I have going on here. Oh yeah, and then so after that, then yeah, when I was in my hotel room, was watching the UFC while doing a little bit of programming on the Game of Life, and kind of got the basic implementation working. So you can see it all kind of simulating here. So the idea that I did for the basic implementation, and this is something that a lot of other people did as well, is they just had one entity equals like one kind of data entity, and then there was also another separate kind of rendering entity, and then each data entity had references to the neighboring entities, just using kind of like a dynamic buffer. So each entity kind of knew its current status, and then it also had a dynamic buffer to reference the entities surrounding that particular cell entity, to see if they're alive or dead, and then it kind of would buffer those for the next iteration to know that if on the next generation that it should be marked as alive or dead. So that was kind of like a pretty common pattern. And so, yeah, I just kind of did that, first implementation, just did stuff all on the main thread first. And then once I got the main thread stuff running, ended up moving over to the multi-threaded version. And then let me just kind of real quickly bring up, I think I had a little bit of things in the commit messages about my performance metrics here. So, going back to the beginning. So 25 frames per second on the 512 by 512 grid, doing main thread. And then when I converted it over to multi-thread, then it was 115 frames per second on the 512 by 512 grid. Yeah. So again, that was just kind of like my first pass at the implementation. And then what I wanted to do as an optimization after that is still by using the one entity per cell, ended up doing what's this called? The Hilbert curve, kind of spawning here. So this is kind of basically what it looks like here is you kind of spawn them in this kind of like pattern, this kind of like cycling back on itself. And this is, again, still using the dynamic buffer. This is just kind of a different visualization where it's more of kind of like a color gradient of kind of like, you can see that it kind of starts in this lower corner here, and then it kind of, is
it's
kind
a
of curving
recursive
around.
pattern.
And it's a recursive pattern. And the idea with this is to basically optimize for data locality, so that when you do this, so first I was just kind of spawning them linearly. So I believe they went up first. So basically it would spawn all these in this row, all these in the next row, or the next column rather, next column, and then just keep going along like that. Now, the potential issue that I saw with that is that, once you get to the point where you have so many entities stretched out that now, when you look at the entities above and below it, those entities are going to be within that same chunk. So those can be accessed very quickly because those are, already going to be in the cache and everything. However, if you're accessing the entities to the left and to the right, and then of course on the corners left and right, then those entities are going to be within another chunk than the one that you're in. So that would likely incur a cache miss or a random access where you're kind of going out to memory. Although maybe again, kind of going back to the concepts of hardware prefetching, maybe the computer can kind of recognize some of those patterns and know that, I'm bringing in data from those kind of neighboring chunks. So again, what this was me trying to optimize is data locality, so that the physical positioning of these data entities were all very close to each other. So now that you see, like if I look at, say, this entity and look at its neighboring entities, you can see that pretty much all these entities were spawned within like a pretty close proximity to each other. So very likely all these entities are going to be within the same chunk. So the idea was to kind of optimize for that, so that, my thinking was that the entities kind of surrounding this entity, it'd be a lot faster to access. So the interesting thing was, though, is that my performance actually ended up being quite a bit worse. So what I had kind of noticed is I kind of made a little basically tool to determine the what I call the hit rate of basically cells that are checking neighboring cells that live within the same chunk. Now, with the linear implementation, there's a hit rate of only 25%, which makes sense because you think of the entities within the same chunk are only the entities above and below. So that's 2 out of 8 neighbors, which comes out to 25%. So that math checks out. Now, with the Hilbert curve, I calculated a hit rate of 85%. So that basically means that 85% of the time, an entity is checking a neighboring entity living within the same chunk. And I was basically just able to use the, what is it called? The entity storage info to see, what chunk I was in, and kind of compare the different chunks there. So yeah, with the linear implementation, do I say what speed that I was getting? So the linear implementation, I was getting 120 frames per second. Well, here's with the Hilbert curve, I was getting 90 frames per second. So I was very confused by this. I think, Phony kind of mentioned some things here that I think that are kind of the cause for it, is basically because, when we're doing the linear implementation, we're just kind of going to a memory location and then just doing a, straight offsets from that, which is, a lot easier to do than saying, going to, multiple memory locations, even though in theory, those memory locations should all be in the cache. It probably is just a little bit simpler for the computer to just, get those, 3
I think prefetching is
memory
going to get you
locations.
a lot of the way there. Like it will probably prefetch for you in the linear case, whereas you pretty much stopped any change of it prefetching now.
Right. Yeah. Because it's just kind of it just kind of sees this as some weird pattern where I'm just like saying, oh, go to this.
Yeah.
Where, yeah, again, the hardware prefetcher is probably, smart enough to say, oh, this guy is, looking at these things all in this same row next to each other. And yeah.
Yeah, no, I mean, the interesting thing here is that Vulkan actually has I think most GPU languages actually, but at least I very vividly remember having to specify in Vulkan, because you have to specify everything in Vulkan. This is the way that the texture should be stored, and it should be, and the default that you pick is actually the one where it's more tile-based, locality-wise, than just a linear array of pixels going through. So it actually uses something very similar in style to this, because it means that you can effectively go around it, and so you can more easily do like a sand implementation, like a classic sand falling implementation,
Nice.
or cellular automata with this, which this is
what we're doing.
exactly.
So yeah, that was definitely surprising to me, because again, it just goes to show you that, you may have some assumptions about an optimization, and it really only takes testing it out and trying it in practice to see if that optimization is going to work or not. So yeah, I was very surprised with this myself. So yeah, that was yeah probably one of my biggest takeaways from just kind of yeah, doing this challenge by myself. Because most of since the last time that I did it, I think someone had kind of mentioned doing the whole Hilbert curve thing because, again, my kind of assumption was that I was being performance limited by creating bigger and bigger grids to the point where, entities that are above and below or like side to side are outside of the, current chunk that it's iterating on. So, yeah, very interesting.
There's a chance you might still get performance out of having smaller grids where that's the case. I think the problem here is also the fact that it's everything that is part of the Hilbert curve. If you were to do just like a tile has linear and then another tile has linear, then it's more should be more easily able to do that. Be fine. But are we gonna go into what other people are doing?
Yeah, we will in just a second. I just wanted to hit this. So I don't think that yeah, I think I just tested this multi-threaded, but my assumption would be that single-threaded would see the same performance differences. I don't think there would be yeah, any difference for multi-threading for this particular thing.
Yeah.
Yeah, and then so the next thing that I did is basically what I have the project as right now, where I ended up kind of doing a more, call it like a packed version where I'm going to try and explain this as best as I can and, hopefully without losing everybody too much here. But basically I used a unsigned long, which is a 64-bit integer to basically store the alive state of 64 cells. So that basically made essentially an 8x8 grid where I could basically have, cells be alive or dead. And actually, you know what? I'll just go ahead and play this here just to have it running in the background as I'm talking about this. But so that's kind of like the base building block is entities are stored in a unsigned long, again, a 64-bit integer, where cells are either marked alive or dead. And okay, there it goes. And then so then I had that stored in a dynamic buffer component, and then so one entity then had 16 elements of that dynamic buffer, and then so I would have several of these entities for depending on the size of the grid. So that's kind of how I ended up breaking it down, and then I think one thing that I kind of noticed is when I started doing a lot of these kind of like low level bit level operations like this is that entities actually kind of started getting in the way a little bit just because of how I had set things up, because like now I kind of have these like 3 layers of things, which in retrospect is probably not the best way that I should have set things up, but I was just kind of playing with some of the ECS tools in ways that I thought was interesting, so I'm kind of glad that I did it that way. But basically what happens is now when I have a 8x8 chunk of cells, I can simulate that on its own, no problem. But of course we want to expand the grid size, so we need to have these 8x8 chunks basically kind of communicate with each other so that it knows when cells are on one edge of one 8x8 grid, they need to check on the edge of the next one. Yeah. So yeah, what I ended up kind of having to do is now I needed to not only reference the other entity, but I had to reference the index in the dynamic buffer that kind of 8x8 chunk was on. So yeah, just ended up being kind of like a little bit of issues with things that I had to track around that. Which in the end is not really all that bad. Like it kind of makes sense, but kind of getting to that end point There were definitely some hiccups along the way, and I had to do a lot of just kind of like, low level, like bit level debugging. So a couple of tools that I just wanted to point out. Of course, I used the JetBrains Writer IDE. Um, and then I had attached the debugger to the process here, and then was basically just kind of did that, classic John Carmack solution where, just put a breakpoint in and just step through things line by line and make sure that the, program is doing exactly what I think it should be doing. So I was able to kind of like validate things and see where things go wrong, especially in certain edge cases. So that's something that was super helpful for me to do. And then I also kind of use this in tandem with this little application here. This looks horrible on this screen.
There's some scaling issues there.
Let me take a screenshot of this on the other screen and show you what this is all about. So this is a little program called Speed Crunch. Learned about this tool from, we talked about him already, Casey Muratori. This probably is too small for it, but it's basically a calculator.
If you could zoom in, that would probably also help.
Well, yeah, I don't think I can zoom in on this application. I'll do this. We'll save this.
Just do Windows Shift S, which will, use the window snipping tool instead, which will actually let you zoom.
There we go. How about that?
Yeah, there we go.
Okay. So this is called Speed Crunch. It's basically a very fast calculator. And then you can see at the bottom here, there is basically a kind of like bit calculator. So what I could do is I could basically punch in the specific bits, because again, each bit maps to a cell. So if a bit was, say, if like the 0 bit was on, I could click the 0. If like the 7 bit was on, I could click the 7. And then basically I can do all this, and then it gives me what the unsigned long value should be. So this was kind of interesting. I did this for a couple things. One of them is just kind of my like initial testing, where what I could do here is inside the, I guess this would be in here. On this here, I had a starting value, and then by setting this starting value to this 394500, that would create a glider, and then I could like test with a glider, which, if you're familiar with the Conway's Game of Life, there's these different kind of like, patterns that you could create. And so glider is one of them that just kind of like goes across the screen. And so this is a good way that I was able to test the Game of Life to make sure that, as I'm going across those cell boundaries, that things are, simulating appropriately. So I was able to kind of, again, use this Speed Crunch program to kind of craft these to make sure I have the correct starting value where all the bits are in the correct location. And then again, as I was going through and debugging, I was able to see like, okay, so this next bit should be on. Let me go ahead and, select this, and then I could, verify that the, unsigned long value is correct after every iteration. So this was super helpful for me to use as well. But it disappeared. Oh, I guess it disappeared when I opened the subscene here. But I am overall decently happy with my implementation. I do have a bit of a memory leak here, which I haven't gotten a chance to track down. As you can see, that it's just kind of slowly going up and up and up. I still am using a pretty naive rendering solution. It's still just a single quad entity per data cell. So, not necessarily the most efficient, and then I'm just setting the color of them using the material property color overrides there. As far as performance goes, I believe I was able to simulate a 1024 by 1024 grid at around whatever this was running at. 30. I'm doing like some screen sharing and stuff, so I think it was a little bit more, maybe 45-ish for a 1024 by 1024 grid. So Pretty decent performance numbers, I would say. Um, but yeah, that's kind of like basically my main implementation. There are of course things that I would want to do differently and try otherwise, but I think this is kind of a good enough base to work off of for now to maybe test some things off of later.
Yeah.
But do you have any thoughts on my implementation before we move on to some of the other things?
I mean, I definitely recognize that I would have done things very differently than you would. Because, like, I think my main approach would probably have been to start with a binary array, which is something that is in our native collection package, that lets you basically just have one big array of bit data, and it will obviously always use like a byte underneath, so it will have to allocate a byte every time, but it does allow you to have n amount of bits, and then you can assign them and you can check against them, and I would immediately start using that as my grid cell. So all 1024 times 1024 would already be in the bit array, just one long array, and then once I have that, I will then loop over. I would start by maybe having an I job 4, and in that I job 4, from an index calculating which xy value you are at is very easy.
Right.
Because it's as simple as doing a modulo and a division operation that will get you the xy value, and then you can just plus, minus, and that will then you will then be able to calculate that back to the index very quickly, so you get all the surrounding cells. And so you can do the simulation itself just in the binary array. And then once you have done the simulation, then you need to figure out, how do I do the visualization? Well, okay, one way to do that is either I'm going to have an entity represent every one of them, and then I'm just going to loop over. Again,
Yeah.
I'm just going to have a native array. Basically, when you instantiate, when you go to Entity Manager instantiate, you can actually pass in an array. Say you were to pass in an array that is the size of the binary array, it will then also make sure that array you now have actually contains every single entity. And so now your second pass that you're looping over could simply loop over every single like index, and then it will assign that. And you can even do stuff on top of that. You can make sure that it's already archetype based, so you can loop over every archetype. And then realize, hey, maybe I just need to have an entity represent 8 bits at once, or maybe even more. That's probably the approach I would have taken, instead of trying to make the algorithm more complicated with a Hilbert curve and start making, this entity represents. I think I would focus more not on the simulation. The simulation is very easy to do with just a binary array, and I wouldn't recommend anything.
So don't even really use entities for that portion almost.
Exactly, because that overcomplicates it. That should either happen there, or I guess technically it could also happen on a GPU. But for the point of this project, it should still happen on the CPU. But having it happen on the CPU should really just be a binary array. There shouldn't be more to it, because that overcomplicates it. That's how I would have done it. I actually did do Game of Life like in 2016. It was one of my first games. I just remembered, like, during the stream, that one of my very first games was at a camp called Game Development Camp, and we made this game where the point was to that there would be a display grid that basically, like a casino deck that with like poker chips on it, and you would have to guess what how to make that pattern. So basically, you had to like put down pogo. What are they called? Like the discs that you put down in poker.
Poker chips.
Yeah, poker chips. So you had to put down poker chips, and then press a next button. And when you press the next button, it had to match up with the pattern that was already drawn. So you had to sort of guess how to make it result in the next iteration. Which was a fun game. I might be able to show it if I get it working during when we show off everyone else's stuff.
Cool.
But yeah, so I apparently have made it before, but it was way more inefficient. Like imagine it was game objects, and imagine that every game object had to know about every other game object, and it was pointing. This is like Kid Daniel.
Yeah. Yeah. Yeah, no, but your kind of initial thoughts on how you would go about implementing it with the bit array and everything, that seems, yeah, like a nice solution. Again, I kind of just wanted to do some more experimenting with more of the, ECS kind of based features of the language and everything like that. Which again, like I mentioned, I kind of ran into some challenges from those, and yeah, probably would have done it differently. Yeah, if I was kind of optimizing just for performance. But again, I think I learned a lot, and yeah, I was very happy to kind of do this here.